Okay, we have established that an object moving at in a circle at a constant speed, okay, and this can be in this direction or in this direction. If the object is moving at a constant speed, the velocity is not constant. The acceleration responsible for the change in direction and velocity, we call it a centripetal acceleration. It is an acceleration along the radius. We have it here as a sub r, and what's special about that acceleration is that it is equal to the speed squared, v squared, over the radius. Essentially, we have a bonus there, an easy way of finding the magnitude of that acceleration. Again, remember, that's the acceleration that's responsible for just changing the direction of the velocity. One might ask, what if my object here, instead of moving at a constant speed in that circle, what if it is speeding up or slowing down? What we need to remember here, if it's going to do that, we are going to have different accelerations contributing differently. Essentially, remember, to simplify the way we solve problems, we break things down. In this case, we'll break down the acceleration into an acceleration that's responsible for changing the direction, and that's the centripetal acceleration. And then we will talk about the acceleration that is responsible for speeding up or slowing down. Okay, let's see. So for example, in this case here, so what do I have? The velocity here is represented in red, and you see it getting larger. What we have learned from the past, okay, first from the previous screen, since the direction is changing, I must have a centripetal acceleration. That centripetal acceleration is radial. In here, it's going to point this way. In here, it's going to be equal to v1 squared over r, where this is v1. In here, that centripetal acceleration is going to be v2 squared over r, where this is, I forgot the 2 here, v2 squared over r, where this is v2. Here, if this is v3, this is the acceleration. It's going to be v3 squared over r. Again, remember, this is the acceleration responsible for changing the direction. This is the centripetal acceleration. However, since the object is speeding up, remember what we have talked about when we talked about kinematics. For something to speed up, I need to have an acceleration in the same direction as the velocity. Which means, I'm going to take another color here, which means I'm going to need another acceleration that is in the same direction as the velocity. Now, this acceleration, these green arrows I drew, they are tangent to the circle. They are along the same direction as the velocity, so they are tangent to the circle. So, the acceleration responsible for the speeding up around the circle is going to be a tangential acceleration. It's in the same direction as the velocity. What if my object is slowing down? Same kind of idea. Here, instead of having the acceleration in the same direction as the velocity, it has to be opposite in direction. In green here, I'm drawing the acceleration. It has to be opposite to the velocity. So that's the tangential acceleration responsible for the slowing down. Of course, we still have here our centripetal acceleration, and in here, if this one is v1, it's going to be v1 squared over r. If this one is v2, it's going to be v2 squared over r. And if this one is v3, it's going to be v3 squared over r. we didn't discuss yet the values of the tangential acceleration. We just spoke of their direction. That's the important thing. But with the centripetal acceleration, we can find it easily. It's just v squared over r. So in summary, what we are saying, if an object is in a circle, going in a circle with a non-constant speed, it's going to have both a tangential and a centripetal acceleration. So the overall acceleration is a combination of both. A sub r, the centripetal acceleration. A lot of people would write it a sub c for centripetal, and it's all right either way. And a sub t for tangential acceleration. The centripetal acceleration, what I wrote here in blue, is responsible for changing the direction, and the tangential acceleration, that's going to be either parallel to the velocity or opposite to the velocity, is going to be responsible for changing the speed. The overall acceleration then is going to be the sum of both vectors, so it's going to be neither tangential nor radial. But that's not really as important for us here, as long as we remember what's responsible for changing the direction and what's responsible for changing the speed.